Hello everybody, this is a new course on RF microelectronics. We will start with tuned amplifier. Then as we move ahead, we might cover active inductors, mixers, LNAs designs, and how to simulate that, and how to plot the figure of merit in cadence, right? Okay, the first circuit which we saw this in our analog IC design course, that a Cascode amplifier has got a better bandwidth because it doesn't suffer from Miller effect, right? So because from this node to this node there is no gain if the GM of both these transistors are same, so the signal doesn't get amplified, so the gate capacitance doesn't get amplified by the Miller effect. Okay, so these kind of cascode structures are better suited for RF applications. But then the gain of this cascode amplifier is given by GM of this transistor into RD approximately, right? So the GM RD. So this is how. So there is no frequency selectivity here, right? So from in this frequency band, if you see here, the frequency the gain remains constant, and later on at very high frequencies, okay, the gain can drop because of the capacitances, right? All here there could be some poles, and but there's no frequency selectivity, right? But in RF applications generally we don't want such a flat band structure, right? Gate plot. We want that the circuit should amplify only the desired signals, and rest of the signals should be attenuated. Okay, that's the primary requirement of any RF circuit. Okay, so to get that selectivity, what we can do is, instead of an RD out here, we can make an LC network. Now, if you see, this is any inductor will have some kind of resistance also when you make it in the VLSI circuit. So this is how the equivalent circuit looks like, and at a frequency of L is equal F is equal to 1 by 2 pi root, right? If I write that equation, right, at omega is equal to 1 by root LC, okay, this impedance and this impedance gets cancelled, and you just have the resistance. No, they are not the same. That I'll discuss that equation. So this is just an equivalent circuit. So if I plot the impedance, it will look like this. Okay, for the resonant frequency, the impedance will be high, right? Given by this, and hence the gain also will be high only for that particular resonant frequency, right? So just by replacing R with an LC network, I can select the desired frequency, and that desired frequency, where the signal needs to be amplified, that can be defined by this equation, omega is equal to 1 by root LC. So by appropriately choosing L and C, I can design an circuit. It can be called as an LC tuned circuit. Okay, so we can tune it to amplify just the desired signal, right? But then once these are fixed parameters, right, L and C, so I can't tune it. Okay, so it is just it is tuned once, and once fabricated, it will remain fixed. Okay, the resonating frequency remains fixed, right? But if I want to tune it dynamically, even after fabrication with some control voltages, so I can use a MOSFET gate capacitance. Again, this I have discussed in detail in my VLSI design class, where the MOS capacitance, if I leave across the source and the drain between the gate and the bulk, if I apply a voltage out here, okay, the capacitance curve would be like this. Okay, so the MOS capacitance. So these details are available in the so this can be used as a varicap, okay, variable capacitance, where the capacitance of the MOS, this capacitance can be changed with the help of potential applied between the gate and the body. Okay, so I can, this is an amplifier. Again, these in I have used these resistances and this resistance to match the input resistance to 50 ohms. That I will discuss when we discuss the design of LNA subsequently. Okay, let's just first focus on the tunable aspect out here. Here, if you see, this is the L, and this is the C. Okay, so this C, what is shown here, is now being implemented with the help of a MOSFET, and the potential being applied is onto the gate out here. Okay, so this can be tuned to an whatever frequency we want. So if you see here, for different tuning voltages, okay, the resonant frequency is changing out here. So this can be done. So this is how we can implement an LC tunable circuit by using a MOS varicap. Okay. Now, if you see this is what an capacitance and an inductor, okay, which will have a resistance here out here. So if this resistance, the all practical inductors will have a resistance in series, because once you implement it on an VLSI chip, so there will be some resistance, like you have to draw a spiral using any metal, and that's how you implement an inductor, and if you do that, there will be some resistances. So this is the equivalent circuit. Okay, now if I write the this is the total impedance, and if you see if you if you just write this, this is the total see parallel resistance. Okay, now this is the series resistance, this is the physical series resistance, this is the equivalent parallel resistance, which can be written by this formula. Okay, so so this will be the total impedance. Okay, this capacitance, resistance, and the inductor resistance, this is the this is the parallel resistance. Okay, actually there is no parallel resistance, it's a series resistance. Okay, equivalent this is the equivalent circuit, so I can write it like this. Okay, now at the resonant frequency where omega is equal to 1 by root LC, so these gets cancelled, and this is the equivalent resistance impedance of this particular circuit. Now if you see, this is proportionate, it is proportionate to the frequency, right? So there is a frequency component also involved in the net equivalent impedance even at the resonant frequency, and because of which, if you see here, okay, the impedance as the frequency is increasing, then the gain is increasing out here, right? Gain is GMRD, and later on because of the other poles, it is decreasing, but from here to here, if you see that as the frequency is increasing, the gain is also increasing, right? If you have a tunable circuit just like this. Okay, now you understood, right? So this is an parallel circuit, this is an RLC parallel circuit. This is what actually we can implement on a VLSI chip, because the inductance will have a series resistance. That series resistance this is not a physical resistance in parallel, it is just an equivalent circuit, and that value is given by this particular formula. And here if you see, it is an it has got an omega, that means the total impedance at the resonant frequency is dependent on the frequency. So you might get it. So if you want to have a relatively a constant gain for various frequencies, as I keep, now the capacitance is a variable, right? The MOS capacitance here. So here, if I want this capacitance, I want to change this capacitance, and I want different frequencies, but I want the resistance, the gain to be more or less same. I don't want a gain to change like this. Then what I can do is I can insert a parallel resistance here. This is not the equivalent resistance, mind you. This is an parallel resistance which I am putting. Okay, and that should be much lesser than RSQ square. RSQ square is nothing but this particular parallel resistance. Okay, equivalent parallel resistance. Then at the resonant frequency, the impedance will be decided by this resistance, and not by this formula. Okay, because this R is going to come parallel to that resistance, and since this is much lesser, so now at the resonant frequency, this gets cancelled and Zin becomes to R. So I have to put an R which is much lesser than the equivalent parallel resistance. Okay, but the overall gain will be lesser, but still I can do some kind of gain stabilization. Okay, so this is known as gain stabilization, and now we will do some cadence based simulations and try to understand how to make tunable amplifiers. Okay, so this is a tuned circuit. It's an CS amplifier where the load is an tank circuit. Okay, the tank circuit is made up of an inductor, and I have used an 5 nanometer 5 nano Henry inductor out here, and both these transistors are 45 nanometer technology. So I have kept the length as 45 nanometer. 1 volt is the power supply which I have used here, and I have kept the width as 3 micro for these two transistors. And this is the tunable MOSFET. This resistance I have not yet connected, so it's hanging out here. So this is the tunable MOS cap, right? So I have kept the width as a variable W out here, right? And length I have used. Again, you require a large capacitance so that uh, the tuning range is in few gigahertz or around 1 gigahertz. So I have kept an length also pretty high, 10 micro. So I require a large capacitance out here. So that's the reason. So I go to, so this is an like CS amplifier. I have biased it at around 1 volt is the power supply, so I have used 50-50 and around 0.5 is the biasing voltage here, because the threshold voltage is around 0.3 volts. I have just kept a 0.2 volt overdrive voltage. So and 50 milli AC signal is given here. Both these transistors are of 45 nanometer with 3. This is an inductor of 5 nano. This is presently hanging. We'll see what's the effect of connecting that 1K resistance. This is a MOS cap. So if you see, the source and the drain terminals are open, and the supply is given. The tuning voltage to change the capacitance is given in the body of this. So that I have given as V tune. Okay. So I have taken these two DC operating points for V tune as 1 volt, and I have taken the width, the DC operating as let me do first do an parametric analysis and see what happens. So in the parametric analysis, okay, I have copied these two variables out here. So first let me sweep the W and see what happens. So I'm sweeping W from 200 to 200 micro to 1000 micro. So in 5 steps, right? So I'm doing an AC analysis and trying to plot the output voltage here. So if you see here in the analysis option, it is AC analysis. Okay, I'm not doing a transient analysis, and I am expecting that the resonant frequency to be between 500 megahertz to 15 G. So that's the range I have selected. So let me do an parametric analysis. Now, if you see here, okay. Now I get for varying width. Okay, I am getting here. Now if I see here, if the width is large, okay, the capacitor, the tuning frequency is less. Okay, so that is what is expected, right? If you increase the width, the capacitance increases, and the tuning frequency is given by an omega is equal to 1 by root LC. So the C is in the denominator, and since it's in the denominator, as the width is increasing, the tuning range is coming down. So this is what is expected. So if you see here, if I put a marker out here, this is around an 1.14 gigahertz, and this is around 810 megahertz, right? And this is 674 megahertz. This is 574 megahertz, and this is around 511 megahertz. Okay, I'm giving a 10 millivolt signal, so all of them have got more than 100, right? So the gain is also varying. So if you want to stabilize the gain, right, now what we can do is, if that is the requirement, because actually with the for various different frequencies, the overall gain of this amplifier also changes because of the high frequency response. So if at all I am interested in stabilizing the gain, I can put an low resistance out here, relatively low resistance out here. But the problem is the gain will be lower. Okay, but then I can stabilize the gain. Okay, so I'm connecting an 1K out here, and if I do a parametric analysis, so you would see, okay, the gain are more or less the same, right? It's somewhere around from 80 to 100, right, for the same frequency. If you see, the frequencies have not changed, and but that resistance 1.14 and 511. Okay, but the gains are okay. So so I can change the but obviously this is just to understand the variation of what is the effect of variation of W on the resonant frequency. When I say tuned circuit, obviously that is not what is going to be varied. For a tuned circuit, this is the tuning voltage, okay, V tune. We need to change this and see where. So that's what I'm doing. I'm going to do now. I'm going to change the tuning voltage, okay. I'm starting from 0 to 1, and if I am running that, so now you see this, okay, for the tuning voltages. So M, it is around from 1.47 to, okay, 1.1, right? So with the tuning voltage, okay, so I am able to change the resonant frequency. So I can accordingly tune my RF amplifier to the desired frequency, right? So this entire thing can be shifted to right, the mid frequency wherever, right? Suppose this is what 1 gigahertz, right? Now this I am tuning around 1 gigahertz, okay? Say, let me put it here. So I am tuning around 1 gigahertz. Then I might want to use this W as 200. Now suppose I want an amplifier which is which I want to tune around, say, around 500 or 600, then I can keep this as 1000, right? If I do that, okay, so let me do a parametric analysis out here. So now I have chosen I have selected the W to be W to be 1000 micro, right? And hence I will find this entire thing is shifted in the frequency of this band, right? So if you see here, this is around 600 megahertz, and this is 650 megahertz, and this should be around 511, right? So this is how I can, right? So there are two things. First, you need to appropriately select the width of the transistor, and obviously the resistance also, the inductor value also, to get it in the proper band, and within that band you can change, you can get the desired frequency by applying appropriate tuning voltage, right? So let's give me one more example here. If I change this to say 500 micro, and then I do the parametric analysis by changing the tuning voltage, right? Now if you see here, the mid band voltage is around 800 megahertz, right? So I can tune somewhere from 800, it's starting from 730 to around 930 megahertz, right? So different, I can tune it to wherever, whichever frequency I require, right? So what we have learnt out here is, first, to choose the appropriate width and the inductor value. It is dependent on the inductor value also, to select the appropriate course band, and within the band, if I want to do fine tuning, I can use this tuning voltage, right? This resistance I have used for kind of gain stabilization. Another thing which we need to remember is inductors. The moment you make spiral inductors on a VLSI chip, it will have a series resistance, right? So doing a simulation and getting the results with an ideal inductor would not be good enough. Because once we make an spiral inductor, there is bound to be some series resistance. So I put an R is equal to 10 in series. Okay, I'm taking. So what this is going to do is, this is going to spoil my quality factor. Okay, so if I do a parametric analysis now with that resistance, so you will find that so this is what the plot. Now again, the frequency with this is with the different tuning voltages. Okay, the tuning frequency is again from 774 to, right, 974, around 200 megahertz. This I am able to change. But if you see here, the bandwidth, okay, the quality factor, the bandwidth has increased, or the quality factor has deteriorated. right? Now, what is quality factor? The ability to select a particular frequency, right? Now this is more rounded off. If you see, all these things are more rounded off. So there is a possibility that the adjacent signals also will pass through. So the selectivity has deteriorated, right? So whereas if you just do a simulation with ideal inductor, we got sharp peaks, okay, and those peaks they indicate that it is able to do and fine, very fine selectivity. So in the other way around, if you want a wide band amplifier, then you may want to add an series resistance also to get a wide band amplifier. Okay, that's an other way of looking at it. If the application says you want a wide band amplifier, so if you want to increase the bandwidth, so what we can do is we can increase this resistance, right? So suppose I want a very wide band amplifier, so maybe I'll put an additional resistance here. Maybe let's see what happens with that. So if I increase the resistance out here, okay, so this is going this coming below this, so let me not increase to that, to around 50. Let me just increase it to 20. Okay. So you see the bandwidth. Okay, I have to do a parametric analysis. So you see the bandwidth is further increased, right? So that is what. So if you want to have a wideband amplifier, so one of the options what you have is to insert a resistance out here, right? So this is how we can design an RF tuned amplifier using a MOS capacitor and giving the tuning voltage to the body of the MOS transistor. Okay, so in the next class probably we will discuss something known as active inductor. Okay, so the active inductor is going to have very high Q of the order of, okay, so if you see these Q might be of the order of, if you take the center frequency divided by the bandwidth, so it could be around 5 or 10 maximum. So if you want a bandwidth, or you want a very high quality factor, say of 100 and above, so active inductors is an option, and in the next class we will discuss about active inductor. Thank you.